In this lesson, we're going to learn how to solve any equation that involves a radical expression. So to keep in mind that in order to solve an equation, we're trying to find all the x values that are going to make that equation true. So if the equation ever has a radical in it, we simply want to isolate that radical, and then we can raise both sides to whatever power is going to eliminate that radical. So let's take a look at this first example. Notice it involves a square root, so we want to get that square root alone on one side. So the first step would be to subtract 6 and make that equal 3. So now if the square root of x minus 2 is equal to 3, then we should be able to square both sides, and that's going to cancel out that square root. So notice that x minus 2 is equal to 9, and therefore if we add 2, we get that x is equal to 11. Now when we have equations involving radicals, as we'll see in the next example, you should always plug that quantity in just to make sure that it in fact works. Because oftentimes when we raise both sides of an equation to an even power, we might get solutions, they're called extraneous solutions, that are basically extra solutions that don't work in the equation, even though the algebra ended up getting us to that particular point. So if we plug in x equals 11, then 11 minus 2 is 9. Square root of 9 gives me 3. So sure enough, 3 plus 6 is 9, and it works. Let's take a look at another example, however, to where whenever we square both sides of that equation, we're always going to get some equivalence, an equivalent equation. Unfortunately, the original equation might not have the same number of solutions as the new equation, and we're going to see that in a short second here. So here we have an equation where we have a square root involved again. So the first step is to get that square root alone on one side. Now if we square both sides, notice that squaring the left side cancels the square root, but we'd have to square the right side, which means that we're multiplying x minus 1 times itself. That's going to give me a quadratic expression on the right. So now in order to solve quadratic equations, remember, we simply set it equal to 0 by subtracting all the quantities from the left. And this gives us that 0 is equal to x squared minus 6x. We can now factor out the common factor of x, and when we apply the zero product property, we find that x is equal to 0 or x is equal to 6. So those are our two solutions that algebra gave us by just applying the operations that we should apply in order to solve this equation. But let's take a look at checking each of these values. If I plug in 0 to both sides of the original equation at the beginning, notice that we simply get the square root of 1 minus 1 is equal to negative 2. But notice the 1 minus 1 is 0. And so notice that that one didn't actually work. So x equals 0 is considered an extraneous solution. While if we plug in 6, notice that the square root becomes the square root of 25 minus 1, while the right side is 6 minus 2, which gives me 4. Sure enough, 5 minus 1 is in fact 4. So that means that x equals 6 is the only real solution to this radical equation. Now we can see why this ends up working if we look at the graphs of this equation, or why we end up getting extraneous solutions. And that's because if you look at the original equation, which was the square root of 4x plus 1 equals x minus 1, notice that the left side is simply a radical function, therefore giving you the red graph, while the blue function, x minus 1, is linear. And we can see that if we graph both of those, we're only going to get one solution, because the solution to an equation is simply the x coordinates where the points of intersection occur. But once we square both sides, remember that we get 4x plus 1 on the left, and we get x squared minus 2x plus 1 on the right. So now 4x plus 1 is a linear function, or the red one, while the right side is a quadratic. And notice that the quadratic now gives us two different solutions. One when x is equal to 0, and one when x is equal to 6. So in the original equation, we only had one solution. While on the right one, once we squared both sides, we got an extra solution that's not actually part of the solution set of the original. So notice that the other solution we get, which would be x equals 0, is simply called extraneous because it's an extra solution. Let's take a look at one last example to where we end up having two radicals on both sides, or rather two radicals in the equation. So now we see that if we isolate one radical, like this one right here, then we would have a radical alone on one side so that we could square both sides. But notice that what some students try to do is at this point just square both sides, thinking that that's going to cancel out the radicals. But remember, if I take a plus b quantities squared, that doesn't just distribute the square to both terms. So I can't cancel these until I move one of the radicals to the opposite side. Now I can square both sides. And notice that the left side is going to cancel out the radical to get x plus 3, while the right side we have to distribute, giving me 3 minus root x times 3 minus root x. And when I distribute that, that ends up giving me x plus 3 on the left still, but on the right we get 9 minus 6 root x plus x. So notice in the original equation, we had two radicals. After moving one of the radicals to be alone on one side and squaring, we now only have one radical. So our job now is to isolate that radical term again by shifting everything away from it. So if we subtract 9 and subtract x, that gives us negative 6 equals negative 6 root x. Divide by negative 6, and that gives me that 1 is equal to the square root of x. So now notice that by squaring both sides, that gives me that x is equal to 1. Now we should, of course, check that just to verify that it works. The square root of 1 is 1, and the square root of 1 plus 3 is 2. 1 plus 2 gives me 3, and therefore this works. So in order to solve any equation involving radicals, you simply you isolate one of the radical terms and square both sides. Just don't forget to check for extraneous solutions. So even if the index happens to be 3 or 4, meaning we have a cubed root or a fourth root, just remember that we still raise both sides to whatever power is going to cancel out that radical. Okay? All we need to recognize is that the only time we have to check for extraneous solutions is if we raise both sides to an even power.